Hello everyone, and welcome back to the series on differential equations. Today we're going to take a quick break from solving differential equations and take a look at what I think is very beautiful tool for solving differential equations amongst other applications, and that is what is called a Laplace transform. So you're like, okay, well, what exactly is a Laplace transform? So the definition of a Laplace transform is going to be as follows. So the Laplace transform of some function f of x is going to be another function, but it's going to be a function of another variable. And I'm going to represent that variable as just omega. And this is defined to be the integral transform from 0 to infinity over a function of x times e to the minus omega x. And in order for this to be a function of omega, the variable of integration must, of course, be x. Okay, so this is the definition of what a Laplace transform is. So what I'm going to do is just go through a few examples of how to find the Laplace transform, and we're also going to look at some going backwards examples at the very end. So let's consider the very basic example, the Laplace transform of a constant, 1, 5, 0, number. So that's going to be equal to the integral from 0 to infinity of our constant times e to the minus omega x with respect to x. So the constant can of course factor out, and we're just going to be left with this e to the minus omega x exponential, which is just going to be equal to c times minus 1 over omega times e to the minus omega x, and of course x needs to be evaluated as x goes to infinity and as x goes to 0. As x goes to infinity, this exponential goes to 0, provided that omega is positive, which we're going to be taking as an assumption. So that goes to 0, and then as x goes to 0, the exponential goes to 1, so you have 0 minus 1, which is minus 1, which is going to negate that constant in the front. So what we're going to have is we're going to have c over omega as the answer for the Laplace transform of our constant. So therefore, if somebody asks you, what is the Laplace transform of 5? You're just going to be like, okay, that's just 5 over omega. And you're like, okay, well, what's exactly going on there? So we already know what y is equal to 5 looks like. That's just a horizontal line. That's just y is equal to 5. And over here, in the different domain, in particular the omega f omega world, c over w is going to look like a decay function. Obviously there's some stuff on the left hand side, but omega we're going to be assuming to be positive, right? So the Laplace transform takes a horizontal function and maps it to a rational decay function, right? And this is going to be important in applications a little bit later. Right? So that's one basic function. So let's look at another important class of functions, and that's the Laplace transform of monomial terms. Let's say x to the n, where n is a natural number, but you can actually take n to be any real number as well. So this is going to be equal to the integral from 0 to infinity of x to the power of n e to the minus omega x dx. So we're going to be performing a very small substitution. So let's assume that u is equal to omega x, where omega is a positive number. And obviously u is going to belong to 0 to infinity because x is belonging to 0 to infinity and omega is a positive number by assumption. And also dx is going to be equal to du over omega. So using these transformations on our integral, we're going to have this is going to be equal to the integral from 0 to infinity. X is going to be 0 divided by omega to the power of m times e to the minus u times du over omega. So once we have that, we're going to have n omegas on the bottom here, 1 omega here. So we're going to have omega to the m plus 1 there. And then over here we have the integral from 0 to infinity of u to the power of n e to the minus u du. So we can obviously rewrite this expression here because we have a monomial times an exponential on the domain 0 to infinity. So if you know the gamma function, then this should ring a bell to you. So this is going to be omega to the power of n times the integral from 0 to infinity of u to the power m plus 1 minus 1 e to the minus u du. And this is just a gamma function, right? Gamma of n plus 1 in particular. So therefore, the Laplace transform of x to the power of m is just going to be equal to gamma of n plus 1 all over omega n plus 1. Right? So keep in mind, if n is a natural number, then gamma of n plus 1 is just equal to n factorial. Right? But you can take the Laplace transform of the square root of x or anything of the sorts if you really want to. Right? So that gives us a nice class of functions for Laplace transforms of. So let's just do some baby examples. So the Laplace transform of x to the power of 5 is going to be equal to gamma of 6 over omega to the power of 6, which is just going to be equal to 5 factorial over omega to the power of 6. If you have the Laplace transform of x cubed, that's just going to be equal to gamma of 3 divided by omega 3, which is just 2 factorial, which is just going to be equal to gamma 4 over omega to the power of 4. Let's just erase that before yeah, there we go. Nice, more clean. So gamma 4 over omega to the power of 4, so that's 3 factorial, which is just going to be equal to 6 all over omega to the power of 4. And you're like, okay, well, what's going on here? Well, x to the squared, x to the cubed, x4, x5, x6, x7, and higher, those are just going to be equal to functions that increase at very rapid rates. So what is the Laplace transform doing to these functions? Again, if this is x and this is our f of x, and this is omega and this is f omega, notice that they're still rational functions, but they're decaying faster and faster. So we're going to functions that look like that, and like that. So there's still decay functions and rational decay functions, but the higher the monomial term, the faster they decay in what we refer to as the frequency domain, which the Laplace transform transforms to. Right? So, of course, you don't have to have a natural number as that exponential, right? You can have, for example, the Laplace transform of x to the 3.7, which is just going to be equal to gamma of 4.7, all divided by omega to the power of 4.7. Gamma of 4.7 is just a number. It might not be a pretty number, but it is just a number, and we still have a, in some sense, rational function, which will decay as omega gets close to infinity. All right, so that takes care of constants, monomials, and in some sense that also encapsulates polynomials as well. Let's look at another nice class of functions that we definitely need to understand, and that is exponentials. So Laplace transform of e to the ax. Let's assume we have just an arbitrary right parameter there. So this is going to be equal to the integral from 0 to infinity, e to the ax times e to the minus omega x dx. Same base, so we can combine our terms. So that's going to be equal to the integral from 0 to infinity of e to the a minus omega x dx. Obviously, this integral is going to diverge if a is bigger than omega, but it definitely is going to converge if a is less than omega, which means that a minus omega, that number in front of x, is a number less than 0. So let's assume that that is actually the case. So if that's the case, then we're going to have 1 over a minus omega times e to the a minus omega x, and that's going to be evaluated as x goes to infinity and as x goes to 0. So as x goes to infinity, this is going to go to 0, provided that this is the case. And as x goes to 0, that's going to go to 1. So you have 0 minus 1, which is going to be minus 1, and the a minus w are going to swap algebraic positions. So we're going to have the Laplace transform of e to the ax is going to be equal to 1 over omega minus a, which is only properly defined if a is less than omega. As a basic example of this, let's assume that we have the Laplace transform of e to the 5x. That's going to be equal to 1 over omega minus 5. And if you have the Laplace transform of e to the minus 2x, that's going to be equal to 1 over omega plus 2. Notice that these are also rational functions, but instead of having vertical asymptotes at x equals 0, like our monomials do, we now have vertical asymptotes at omega is equal to some number, where that number was the rate parameter of the associated exponential function that we started with. Now that we have polynomials and exponentials taken care of, let's move on to the periodic trigonometric functions, in particular sine of x. So let's assume that it has an arbitrary little rate parameter a, so we can keep it as general as possible. So since we already know how to do the Laplace transform of exponentials, I want to start off with a complex representation of sine. So that's going to be equal to the Laplace transform of e to the iax minus e to the minus iax, all divided by 2i. 2i is just a number, and you can prove that the Laplace transform is a linear operator, so constants can factor out. So we're going to have 1 over 2i times the Laplace transform of e to the iax, and then minus the Laplace transform of e to the minus iax. Right. So we've already proven that the Laplace transform of e to the alpha x is 1 over omega minus alpha. So this is just going to be equal to 1 over 2i times 1 over omega minus ia minus 1 over omega plus ia. We're just going to get a common denominator here. So 1 over 2i times omega plus ia minus omega minus ia, put them in parentheses just to be safe, and then omega minus ia times omega plus ia, once you FOIL and cancel out common terms, is just going to be omega squared plus a squared, and keep in mind if you don't remember, I squared is equal to negative 1. So once we simplify the top, because notice that we have this omega minus omega term, so they're going to cancel out, we're going to have ia plus ia, which is 2ia, and the 2i's are going to cancel. So therefore, the Laplace transform of sine of ax is just going to be equal to a divided by omega squared plus a squared, which is still in some sense a rational function with a constant on the top. A couple other little algebraic exercises that I'm going to leave for you just for fun because the proof in some sense is not that much different. Would be the Laplace transform of cosine of ax, the Laplace transform of hyperbolic sine of ax, and the Laplace transform of hyperbolic cosine of ax. These three functions are related. So, the Laplace transform of cosine ax is similar to the Laplace transform of sine, except instead of a on the top, it's going to be the variable omega on the top, with omega squared plus a squared on the bottom. And if you know any relationships between sine and hyperbolic sine and cosine and hyperbolic cosine, you should remember that there is some factor of I that can be represented as a substitution. So one can show that this is equal to a over omega squared minus a squared, and this is going to be equal to omega minus omega squared minus a squared. So those four identities are going to be very, very useful if you have solutions for differential equations that are periodic. Now, one super theorem is going to be the following, and that is the Laplace transform of the product of two functions, in particular ax times some function of x, is going to be equal to the Laplace transform of f, but instead of evaluated at omega, it's going to be shifted to the right by a units. So here, the Laplace transform of f of x is equal to capital F omega. So what we have here is multiplying a function by its exponential and then taking the Laplace transform of it is the same as just doing a horizontal shift of the Laplace transform. Right? So it shifts the Laplace transform horizontally. Right? So a multiplicative transform in the spatial domain equals just a arithmetical transformation in the frequency domain. And there's a lot actually going behind the scenes there, but at least appreciate the beauty of that from the algebraic side at least. All right, so since this is a little weird at first, let's do a few examples just to make sure we get at least algebraically what's going on here. So let's assume that we have the Laplace transform of e to the 7x times x to the fifth. So what you really need to focus on here is the Laplace transform of x to the fifth, and then shift that horizontally by whatever factor that rate term is for that exponential function. Okay, so e to the 7x times x to the fifth, because if it was plus, we would just distribute that linearly. So we know the Laplace transform of x to the fifth is going to be gamma 6 over omega 6, right? So this is going to be equal to gamma 6 over omega 6, But instead of omega 6, we're going to be shifting it to the right by 7, right? So that's going to be omega minus 7 to the power of 6. And if we have the Laplace transform of e to the minus x times cosine of 4x, keep in mind cosine's Laplace transform has a variable on top. And notice that we're going to be shifting things to the left 1 unit. So that's going to be equal to omega, instead of omega on the top, because remember the Laplace transform of cosine is going to be omega over omega squared plus that rate parameter squared. Now we're going to be shifting it to the left 1 unit, so that's going to be omega plus 1 squared. So you can write that in simplified form as omega plus 1 all over omega plus 1 squared plus 16. And you can FOIL that omega plus 1 squared out and combine the 1 with the 16 if you really want to. Similarly, if we have the Laplace transform of e to the minus 2x times the hyperbolic sine of 3x, that's going to be equal to 3, because remember sine and hyperbolic sine has a constant on top, over omega plus 2, the quantity squared. Hyperbolic sine has a minus sign in the middle, minus 3 squared, which is 9. And then the Laplace transform of e to the 4x times, let's go hyperbolic cosine now, of 7x. That's going to be equal to, so variable on top, so it's going to be omega minus 4 all over omega minus 4, the quantity squared, and then minus 7 squared, which I guess we can just write as 49. Right? So that's what happens when you have the Laplace transform of the product of two functions, where one of those functions is just a simple exponential growth or an exponential decay function times some other function, which hopefully we know the Laplace transform of. The next function that I'm going to introduce is called the unit impulse function, and this comes a lot in a lot of physical applications where you just have something that happens automatically and just disappears in terms of its effect, like a shock wave or an earthquake or a sudden impact of something. So what the unit impulse function is defined as at least one of the common ways, is delta x is equal to infinity for x is equal to 0 and 0 for x not equal to 0. So if we were to give this a graph in some sense with a vertical line with a infinite break there, right? So what we have here is a horizontal line with a hole there, and it sort of goes up to infinity there, right? So 0 here, infinity there. And you're like, okay, well, what's so special about this? I mean, it sort of like looks like the Laplace transform of 0, which might be 0, but does this infinitesimal little point at infinity really make a difference in terms of its Laplace transform? Actually, yes, and that's why it's very interesting to look at the unit impulse function from the frequency perspective, because although it doesn't look significant from the spatial domain, actually a lot can be understood from the frequency domain for this particular type of phenomena. So what we're going to look at is a limiting version of the unit impulse function, which I'm going to abbreviate by delta subscript epsilon of x, which is just going to be equal to 1 divided by epsilon for all x in the interval minus epsilon to epsilon, closed interval, and 0 provided that the absolute value of x is greater than epsilon. Right? So you might want to pause this video and see if you can graph this particular function. So what's going on here is, so we're going to go from minus epsilon to epsilon, so it's going to be a piecewise function. Keep in mind, epsilon is just a number, so 1 over epsilon is just a number 2. So we have a 0 function, and it's not inclusive, so we're going to have open circles there. And then we're going to have a constant function up here, so closed circle of course, and closed circle of course, and this y value is going to be equal to 1 over epsilon. Right? So y equals 1 over epsilon, and this is going to be y is equal to 0. Okay, so one can show that as epsilon gets closer to 0, this line is going to move in, and as epsilon gets closer to 0 from the right-hand side, 1 over epsilon gets super big, so this line is going to shrink inwards and also move upwards as well, right? So it's going to sort of converge in some sense linearly as we track through our epsilon as time. It's going to sort of shrink but move up at the same exact time and approach that particular value. So we can say that the limit as epsilon approaches 0 from the right-hand side of delta epsilon of x, this is actually equal to the unit impulse function, delta x. So what we're going to do is we're going to find the Laplace transform of this limited version of the unit impulse function, and then we're going to be taking the limit as epsilon goes to 0 from the right of that Laplace transform, and that's going to give us the Laplace transform of our unit impulse function. So let's see if we can take a look. You might even want to try this on your own to see if you can get it, but if not, you can just sort of walk through this with me, and we'll see where we go. So the Laplace transform of delta epsilon of x. So this is going to be equal to what? So by definition, that's the integral from 0 to infinity of delta epsilon of x times e to the minus omega x dx. So this is a piecewise function, and keep in mind we're going from 0 to infinity in terms of x, so the left-hand side of that graph doesn't matter. It's just the right-hand side of that graph that matters. So it's a piecewise function with breakpoint at epsilon, so we can break this integral into two pieces. The integral from 0 to epsilon, and the integral from epsilon to infinity, and we're still going to be integrating the same exact function, delta epsilon of x, e to the minus omega x dx. So once we have that split up, then we can start integrating those pieces and their associated y values. So the first piece from 0 to epsilon is going to be equal to 1 over epsilon. So 1 over epsilon e to the minus omega x dx. And then the integral from epsilon to infinity of 0 times e to the minus omega x dx. The integral of 0, or the Laplace transform of 0, or the partial Laplace transform of 0, regardless of what it is, this is just going to disappear to 0. So we're just going to be left with the integral from 0 to epsilon of 1 over epsilon e to the minus omega x, which is in some sense just a partial Laplace transform. So 1 over epsilon is just a constant, so I can factor it out. So I'm going to have 1 over epsilon times the integral from 0 to epsilon of e to the minus omega x dx. So that's going to be equal to 1 over epsilon times 1 over negative omega times e to the minus omega x as x is evaluated to epsilon and as x is evaluated to 0. So once I have that, we're going to have negative 1 over omega epsilon as our leading constant. And then over here, we're going to have e to the minus omega epsilon minus e to the 0, which is 1. Right, and that's going to give us that. And we can get rid of that negative sign in the front to give us a nice representation for the limited unit impulse function. So that's just going to be equal to 1 minus e to the minus omega epsilon, or the minus we over we, omega epsilon. Okay, so that's the Laplace transform of that particular function. Now what we're going to do is we're going to be taking the limit as epsilon goes to 0 from the right, and that's going to give us what we want. So the Laplace transform of our unit impulse function will be equal to the limit as epsilon approaches 0 from the right of the Laplace transform of delta epsilon of x. So that's going to be equal to the limit as epsilon approaches 0 of 1 minus e to the minus omega epsilon all over omega epsilon. And notice that if we try and plug in 0 into the top and on the bottom, we're going to have a 0 over 0, which as we already know is just an indeterminate form. So what we can use is the L'Hopital's rule and find that. So we're just going to be differentiating the top and differentiating the bottom in terms of epsilon. Right, so we're going to be taking the derivative with respect to epsilon of the top and the derivative with respect to epsilon of the bottom. And that's going to give us two new functions on the top and the bottom to work with. So with respect to epsilon, omega is a constant, and keep in mind it's minus omega times that minus, so we're just going to have positive omega times e to the minus omega epsilon, and the derivative of omega epsilon is the variable, so omega is the constant, we're just going to have omega, and we clearly see that our omegas will cancel. So what do we got? So we have the limit as epsilon goes to 0 of e to the minus omega epsilon, and we know that as epsilon goes to 0 from the right or even the left, this is going to go to 1. Right? So the Laplace transform of the unit impulse function is a constant, in particular the constant of 1. The last thing I want to mention today in our little introduction to Laplace transforms is that it must be understood that it's important to be able to work backwards. Because if I give you the function and ask you to find the Laplace transform of, it's just working out a bunch of formulas. But if I say the Laplace transform of some function is equal to this, what was that original function? This is going to be the most important part about at least our exploratory use of Laplace transforms of differential equations. So this is definitely probably one of the most important things you should be able to do, but it can be one of the most algebraically intensive. And notice here I say that it's important to be able to observationally work backwards because there's not at least an easy, generally speaking, way of calculating inverse Laplace transforms from a formulaic approach. So it's sometimes just easy to be able to observe that, oh, this is the Laplace transform of E, or this is the Laplace transform of the unit impulse function, or something along those lines. But if I give you an arbitrary function in the frequency domain, I'm like, what's the original function? Generally speaking, it's not that easy to do. Okay, so what I want to do is just work through just one example, sort of how you would go about it, just to get your basic intuition of what's going on here. Suppose we have the Laplace transform of some function y is equal to omega cubed times omega plus 1 times omega minus 5 times omega squared plus 4. At least for all of our functions up to this point, except for the unit impulse function, the Laplace transform of all of them are rational functions in some degree. So you're like, okay, I have a rational function. Hopefully I know what this original function looks like, at least in some pieces. So one important thing you definitely have to know when it comes to analyzing the inverse Laplace transform of rational functions is to understand how to do partial fraction decomposition, which you probably learned in Algebra 2 or maybe even integral calculus. So if you do a partial fraction decomposition, what you're going to be looking for is you're going to be looking for constants that go on top of this omega cubed term, a constant that goes above this omega plus 1 term, and then a constant that goes above this omega minus 5 term, and a linear combination of things that goes above this omega squared plus 4 term, right? And you can get these constants via a number of ways. Usually systems of equations is the most common way, but one can find that the first constant is going to be minus 1 over 20, 1 over 30, 1 over 21,750, and then over here we're going to have minus 9 omega, minus 16, with an additional constant of 2,320 on the odd-hand side. All right, so that's the hardest part, I think, because once you have a linear series of terms, then it should be very, very easy to find the inverse Laplace transform. Because you're like, oh, 1 over omega cubed, that's like an x squared. 1 over omega plus 1, that's like e to the minus x. Omega minus 5 on the bottom, that's like e to the 5x. Omega squared plus 4 with a variable on the top, that's like cosine. Omega squared plus 4 on the bottom with a constant on top, that's like sine. So the quicker you can make these observations with inverse Laplace transforms, the faster it is to get those particular answers. So obviously what we need in this expression is we need, for example, gamma 3 on the top of this particular expression. So what I can do is I can just ignore this minus 1 over 20 and introduce a 1 over 2 here. So 1 over 2 with a 2 over omega 3, because I know that 2 over omega 3 is the Laplace transform of x squared. Right, and over here, what I'm going to have is just 1 over 30 times, and I don't really need to do anything to this little omega plus 1, because that's just a basic exponential function, right? So I'm just going to write that as 1 over omega plus 1, and then over here, this is just going to be 1 over 21,750 times 1 over omega minus 5, and I'm going to split this omega squared plus 4 up into two terms. I'm going to write it as, let's do minus 9 over 2320 times omega over omega squared plus m4 is the same as 2 squared. And then over here we're going to have minus or plus minus 16 all over 2320 times, and what are we going to have here? So we have 1 over omega squared plus 4. I need a 2 there, so let's introduce a 4 and a 4. So let's do 1 over 4, and then 4 over omega squared plus 4. Right? And the reason I'm introducing that 4 is to get it in the form that I want, right? Because I know that cosine is going to have a variable on the top, so it's 2 squared over, or actually I just need a 2, right? So let's just introduce a 2 there. 2. There we go. So once we have that, we should be set. So let's just inverse Laplace this. So we're going to have that y is going to be equal to negative 1 over 40, and that is the Laplace transform of x squared. So that takes care of that term. Then we're going to have this 1 over 30, which is just e to the minus x. And then over here, that's just another exponential function. So 1 over 21,750 e to the 5x. And this is just a cosine, so that's going to be minus 9 over 2320 times the cosine of 2x. And over here, what do we have? We're going to have, let's see, minus 16 over 4,640 times the sine of 2x. And you probably can reduce that 16 over 4640, which I'm not going to get into. And assuming that I didn't make any careless mistakes here, that would be your original function. And if you took the Laplace transform of that thing, you will get the thing that we started with. Obviously very, very difficult algebraically, but not too impossible for us to do. So that's just a very basic introduction to Laplace transforms that we'll need when we start solving differential equations with this amazing tool. Hope to see you there, and take care.